Matt Sellen, our wise guy, has returned from a semester off. Were we that mean to you last time? Or?
It was awful.
Yeah.
Oh. Maybe the students were. He needed to spend more time with them.
We brought a knife. That was what we did. But, so anyway, welcome back. Thanks for coming back with us.
Thank you. And the knife is actually for physics reasons, not for revenge reasons.
I was going to shift with Ann real quick.
Yeah,
no vengeance here.
That.
So the last thing we did was this, and I'm going to do it again, is that you see that if you drop an egg and you bounce it off a cushion, it just kind of bounces. If you drop it onto this plate, it instantly cracks.
Yep.
And the two big differences between these collisions is that in this case, the cushion kind of nestles the egg and it spreads the force out over a big area as the egg falls, and also it slows the collision down. Those are two very important things. And so you can illustrate this idea that you want the force to be spread out over a big area. You can just conceptually understand very easily by just thinking of a knife. If you want to catch a knife like this, you'd much rather catch it that way than the other way. Yeah, it's got the same momentum either way. It takes the same force to stop it no matter which way it falls, but you know if you do it like this, it's going to poke into your hand and you're going to hurt yourself.
Probably so.
It's because the same force is concentrated at a very small point. Here, that force is spread out over the whole blunt end of the knife.
Got it.
Okay, so that's why when you have a helmet on or football pads or whatever it is, they tend to be very mushy and they sort of spread the force out. So if you run headlong into a wall, your whole entire head kind of absorbs the force, not just one point. You wouldn't expect to have a nail inside of that helmet because that would be sort of bad design.
Yes.
Okay, so the other thing that happens is that the egg slows down kind of gently. So I'm going to toss this egg over to somebody. How about you, Ann?
Okay.
Now notice how you catch that. Throw it back to me. When you catch the egg, you grab it in your hand, so you sort of spread the force out, but you also slow it down gently.
Right.
All right? And it's because the force required to change the momentum of the egg from whatever it's moving at to zero, which is when you're hanging onto it, if you spread it out over a longer time, a smaller force is required. Okay. You get to multiply those two things. So that's why when this thing dropped, it hit all at once, it broke. Here also, it sort of took a longer time.
Right.
And that's why you can throw an egg really, really hard against a sheet. And
I did hear.
Okay, we found, don't take the plasma yet. We're going to cue it up. Go ahead, Ann, cue it up. We found the video from when we did this last time, September of 06.
September, yes, 2.5 years ago.
And this is a class favorite of yours?
Oh, yes. I show this to my class all the time.
All right.
Oh, wait.
Because it is pretty good.
Okay, we can take it now, Marianne. Thank you.
So I was aiming. I'm off
Ann was trying to hit the target and hit the wall above our shot. Look at that. Then Matt's had to hide it and clean it up. And
I throw like Brett Favre.
You threw like a girl in that one. Sorry, Ann.
It's like I couldn't hit the broadside of a barn. So
yeah, and see?
There's the remnants.
There's the remnants. And if you take a look now, we had to take the wall out, Matt. It's because of that. Here it is again. Look at the top of your screen. Slam up.
Ooh,
that's fantastic. So
I can see why the kids love that one.
Yeah.
So now we don't want to have to rip the studio apart. Really.
Well, we got a brick wall now. We can't really move that.
Okay, so that's where we're going to hold the sheet this time. I did bring a sheet. Okay. It doesn't have a bullseye painted on it, but it is green, so maybe that'll help.
Anyway,
do you want a blindfold like the dude that made the half-court shot?
I think that'd be really funny. How about a blindfold?
Okay.
That's all right.
If you're willing to get your seat to me.
Okay, so we're going to hold this thing, and you have to stand way back. So there's a trick to holding the sheet, as I've discovered with my students, because I get them to do this in class. They repeat your experiment, except mostly they hit the sheet.
Right.
Mostly.
Okay, now, so you should stand kind of back.
Even farther?
Well, yes, farther the more interesting, because it would be funny.
Okay.
Okay, and so make it a little harder, and then just throw it as hard as you can. Just wail on it.
Oh.
I'm so nervous.
Hey, all right, you did it.
Good job.
That is fantastic.
Okay. Hey, it landed in the sheet.
Right.
Now,
so, you want to do that again and take a run at it, or you want to do it?
Oh, I don't care.
Can hold it?
You do it. You'll throw it.
Okay. So we want to illustrate here that
hard, because I knew I was going to hit.
You can really throw this thing pretty hard and it doesn't break because the sheet slows it down so gently. Now you really threw it hard.
It's still solid.
Yeah. Ta-da! Okay.
Ta-da.
So what happened there is that the sheet slowed it down gently enough that the force required to stop this thing was small enough that the egg actually didn't have to break.
Okay.
And forces, do we have a minute?
Yeah, sure. We have 1 minute.
Okay, perfect. So forces in collisions can be very, very large. And so the way that you can understand this is, here the force was small because the collision took a relatively long time. And by long time, it could still be like half a second, which sounds like short, but it's really pretty long. If you want to sort of just see how short a collision can be, here's just a golf ball. And I'm just going to bounce it off the table. Just listen. Okay, so all at once, you just heard a sort of snap sound, a click. So that that sound was probably much less than a thousandth of a second. So if you had very, very high-speed photography, you would see that this thing deformed just a little bit and then away it went. If you listen to when you're shooting pool, for example, right, it's just a click. Those collisions are extremely quick. So the forces involved in this collision, the forces involved in billiard balls colliding are really huge forces. So that's why these things have to be built very carefully. So a golf ball is kind of hard to break. You can throw it against the wall and it doesn't break at all.
Golf clubs, however, easy to break. I've done that.
Really?
Not hitting the ball.
Over your knee.
Oh, I see. Was that when you shot a 120 or something?
Yeah, something like that.
Okay.
It went, pew.
Well, Matt, thanks for coming back. We appreciate it.
Well, I'll be back in 2 weeks, and I will actually bring something to blow up then.
Yes.
Awesome. Robert's excited. All right.